Yes, sir. Are you excited?
Yes, sir.
Okay, let's have an organic chemistry showdown. So you should be very proactive. Is that okay? Now, organic chemistry. So, you see, organic chemistry is basically the chemistry. It's gotten from the word. Look at this word, organ. So, where do we see organ? Plants and animals. Do you understand now?
Yes, sir.
So, basically, before now, organic chemistry has an history of, say, it used to be thought to only be gotten from plant and animal sources. Is that okay? Until 1927 stroke 1928, when a certain scientist, a certain chemist named Frederick Wohler. So he was able to synthesize urea from an inorganic source. So before then, they used to believe in what is called vital force, that a vital force was necessary to synthesize organic compounds. Is that okay? So, but since that time, when someone had debunked, no, it's not debunked, he proved it wrong. Is that okay? He proved that theory wrong, or it has no, that he proves the fact that that vital force has no chemical basis. Is that okay? So that was this. It was since then. It was, it became more. The field began to expand, and then more and more studies were done into in the study of organic compounds. Am I clear?
Yes.
So, but primarily, the primary sources of organic compounds are naturally from what? Plant and animal origin. Is that okay? Then another one that occurs naturally is also the crude oil. Do you understand? Petroleum. Do you understand? So petroleum is also, we call those ones, they have a special name. They're called hydrocarbons. They're called what? Hydrocarbons. And they're basically three. Do you remember? They're what? Alkane, alkene, alkyne. Yeah, I'm supposed to even say this. I welcome you to this series. Today we are going to be doing basically everything you need to know about organic chemistry. One, I'll be covering alkane, alkene, alkyne, all the terms, starting from catenation to hybridization to isomerism to, what are those terms? Functional group, which one again? All those guys, octane number, then alkane, alkene, alkyne, alkanol. You see, we have a lot to do. So stick with me as we explore together. And this might be this in fact is the only video you need for your jam. Is that okay? So God will help you as you stick to the end of the video. Amen. Let's go.
Amen.
So we said that that guy was the case. So until 2000, where were we? So let's begin. Now, we discovered that that carbon is able to form a lot of different kinds of compounds. Is that okay? Carbon. That's why the field of organic chemistry is different from inorganic. Is that okay? You see, this is a separate aspect, organic and inorganic. So it's devoted to the compounds of carbon. Is that okay? Compounds of carbon. Basically, there's one that deals with just compounds of carbon and hydrogen, which is hydrocarbons. So, but sometimes we have some other substituents or other group that are attached, such as the chlorine gases and all of that. You get it? So, all right. Now let's discuss some terms that are very, very important. Now, number one term is catenation. The first term we'll be discussing is what? Catenation. What is catenation? Yes. Yes. So carbon has the capacity to form long covalent bonds. Is that okay? Really long covalent bond with itself, and sometimes catenate with other substances. Is that okay? Yeah. For example, in epoxies, you see carbon and oxygen and carbon and carbon and carbon and carbon. Do you understand? While in organic compound, you see carbon and carbon and carbon and carbon. Are you with me? It's 3 already. Okay, then you can go. Okay, from now you soon leave, right? Okay, so we said to form carbon and carbon and carbon to carbon chains. Is that okay? Whether single bonds or double bonds. Is that okay? So that is one thing that is unique about carbon. Catenation. Is that okay? Some other substances also do catenate. Who can give me an example? Sulfur, silicon. You understand? They also do what? Catenate. They form long chains of themselves. Is that okay with themselves and other groups? Are you with me? Now, the second term where our real notes will start from is hybridization. Somebody say hybridization. Now, in order to understand the concept of organic chemistry, you have to understand all these things. First, we now understand that catenation is how that carbon is able to form carbon to carbon single, double, and triple bonds around itself and other compound, other groups. Is that okay? So, around a carbon, we must have how many bonds? 4 bonds. Is that okay? So, if I draw a carbon molecule and I put a double bond here, how many bonds does it need left? Does it need next? It needs 2, right? So we put them like this at an angle. Is that okay? Do you understand? The orientation is very, very critical. You will understand why in hybridization. Is that okay? So it is not, now it doesn't mean you will not be, you are out of, you are totally wrong when you write something like this. Well, at least I don't know, but basically it should be written like this at an angle because there is something about this orientation. Do you understand? Okay. Now, so we know that there must be 4 bonds around a carbon atom. So first, what is hybridization? So from the word hybrid, right? So hybridization simply means formation of hybrid orbital. Hybridization, the concept of hybridization is a model that is used to explain how carbon is able to form those kind of bonds, how carbon is able to catenate. The concept of hybridization. Is that okay? And it was brought about by Pauling. Do you remember Pauling, the guy that worked on electronegativity scale? Do you remember? All right. So it was one that, brought about, used hybridization to explain that concept. So an hybridization is the what? The mixing of what? Of orbitals, 2 or more orbitals to form a hybrid or to form another orbital known as what? Hybrid. Is that okay? Now, carbon in its ground state has this electronic configuration. Make sure you're following me. Is that okay? Carbon face here. Sit right. Carbon in its ground state has this electronic configuration. So carbon is carbon 6, right? So in its ground state, it has this electronic configuration. You are going to have 1s2, 2s2, 2p. Is it talking to you? What's it? Okay, so carbon in its ground state. So this is the ground state electronic configuration. Is that okay? It has 1s2, 2s2, 2p2. Are we clear? So if you want to draw the orbital diagram, the orbital structure, you're going to have something like this now. This is lower energy level, right? So let's bring it down here. This is a higher energy level than that. Okay, so we have 1s2 is going to be 1, 2. Does this make sense? For this next guy, 2s. Then what? 1, 2. But for this guy, p orbital is what? Degenerate, right? Into how many? 3. So we have what? 1, 2. Does this make sense? So we have electrons in what? 2px and what? 2py and 2pz. Now, if you don't understand what happened here, let me know in the comment section. I'm going to release a video on what all of these are. Is that okay? So it's degenerated to 2px, 2py, and 2pz orbitals. Now, in this case, it seems to us as though this guy needed how many more electrons to form bond? How many more electrons to form feel it? No. How many unpaired electrons do we have here? 2 unpaired, right? So it looks as if it needs 2 more electrons. Does that make sense? All right. So what happens is this: when carbon actually wants to form bond, the process of hybridization occurs in 3 possible ways. Is that okay? In the first way, it is used to form the sp3 hybridized. How do you write sp3 by 3, right? Also 3. Okay. sp3 by 3, right? Okay. Now, it's used to form the sp3 hybridization. Now, the sp3 hybridization is this. So carbon in its excited state, here's what it does. The first thing it can do is to promote, because this energy level, you see that they are almost the same, right? Almost at the same level, right? P is slightly higher than S. Is that okay? In orbital level, is that okay? Even in the same energy level. Energy level 2, but P is at a higher energy a little than the S orbital. Are we good? Okay. So, but because they are almost of equal energy, or they are the same energy level, so to speak, carbon is able to promote an electron from this place into this unfilled orbital. Are you with me? So when carbon promotes an electron from here, it's going to become this. Electron configuration becomes this. 1s2 still here, but there's going to be a promotion from here. So one electron will leave here. There were 2 electrons here before, so this was 2s. Now it becomes 2s1, 2px1, 2py1. This electron will be promoted here, then we'll now have 2pz1. Does that make sense? So this electron here has been promoted from this, is of equal energy. Is that okay? So in its excited state, it gains enough energy to be able to promote electrons to this point. Now when it promotes electrons to this point, how many unpaired electrons do we have? We have 4 unpaired electrons. So, and how many electrons have been mixed together? How many electrons have been mixed? We have mixed 1 s orbital plus a p orbital, another p orbital, and another p orbital to make this hybrid that has what? 4 valent electrons. Does that make sense? So this now becomes what? sp3 orbital. sp3, yeah, orbital or hybridized orbital. Do you understand now? So this is an orbital on its own. Does that make sense? So this guy is the sp3 hybridized. Now what will now happen is this: because there are now 4 valent electrons, it means there are 4 unpaired electrons. So because of that, carbon is able to engage in what? 4 more bonds around itself. Is that okay? Or take 4 more electrons from what? A neighboring atom. Engage in covalent bonding specifically. Is that okay? Yeah, we're supposed to talk about that too. Covalent bonding. Is that okay? So now we said for sp3 hybridization, so how many electrons are mixed? How many orbitals are mixed? 4 orbitals. 2 types of orbital, but 4 orbitals actually. 1s, 3 p's. Is that okay? So in percentage, how many s orbital in character does this orbital have? This hybrid orbital. 25% what? S character. Is that okay? 25% what? S character. Why? Because the entire thing is 4. Is that okay? And how many percent P character? 75% P character. Does that make sense? Okay. So in diagram, with this way we represent it. S orbital. What's the shape of S orbital? S orbital. Spherical. The shape of S orbital is what? Spherical. Then plus what? Dumbbell, dumbbell, and dumbbell. Do you understand now? So these are the orbitals that when these 3 orbitals mix, for example methane, methane specifically. So you are going to get a shape that looks like this. So each of them are going to mix with this. Each of these 4 are going to mix with this. So you have something that looks like this. You understand me now? So this is the shape of the new orbital that is formed. Do you get it? So more like spherical and dumbbell together. Do you get it? Okay. Now, what are the other characteristics that this sp3 orbital have? Number 1, it is characteristics of what? They are alkanes or what? saturated hydrocarbons. And we're going to talk about that. Now, when you hear saturated, just think of the word satiated. When you eat and you are okay, what do you say? I'm satiated, right? So you are full, nothing more can enter, right? So think of them as what? Saturated. So saturated, so they are full. There is no more space for accommodation of what? Electrons. Does that make sense? All right, so that's saturated hydrocarbons. They are alkanes. Only alkanes are saturated. Tell your neighbor, only alkanes are saturated. Only alkanes are saturated. All right, now. All right, good. So now another thing about this sp3 hybridized. Another thing about the sp3 hybridized is this. We said that it's characteristic of the alkanes, right? Okay. Another thing about them is that they form only sigma bonds. They form only, or they give rise to only what? Sigma bonds. All right. Thank you. Now, sigma bonds are the strongest what? Covalent bond. Sigma bonds are the what? Strongest covalent. And the sigma bonds, that the specific sigma bonds that are found in these guys, in alkene, they are the longest, and they have a bond length of about what? 154 picometers. Do you remember? Or 1.54 Armstrong. Armstrong is another unit for picometers. Is that okay? And they are the strongest, right? They have an 348 kilojoule per mole in energy, right? What is it? Kilojoule per moles. That's their bond strength. Is it nanometer or picometer? Nano or pico? Okay, I don't know. Maybe, yeah, nanometer, yeah, thank you. I think you are correct. Thank you. So 154 what? Nanometers, which is, I mean, nobody will ask you this, but just know this. Then the strength, the bond strength of that guy is what? 348 kilojoules per mole. Then one other thing about sp3 hybridized orbital is what? Is that they have a bond angle of 109.5 degrees. Does that make sense? Or 109 degrees, 28 minutes. 20 something minutes. Is that okay? And so we're basically 109.5 degrees. Is that okay? And what is the shape that they form? They form a tetrahedral shape. Is that okay? So that's why whenever you see alkanes, you see a shape that looks like this. So basically this one will be drawn like this to show you that it's coming out of the board. You see one that is drawn like this. It's drawn like this to show you that it's going into the board. Is that okay? Then you see another one that is at the other side of this side. So the bond angle between all of them is what? 109.5 degrees, and this shape is what? Tetrahedral. Does that make sense to you? Okay. Now, that's tetrahedral shape. Now, what other thing about them do we need? Yes, this guy also allows for what? Allows for free rotation about the single bond. Do you understand? There's free rotation about for the free single bond. So that's why there is no stereoisomerism here. Is that okay? There's no geometric isomerism here. All right. So that's for the sp3 hybridization. Now let's talk about the sp2 hybridization. Now for the sp2 hybridization, in the sp2 hybridization, first know, carbon is also in its excited state. Is that okay? Well, here's what happens. 1s2 here, 2s2 here. Are you with me? If I draw something like this, whose rule have I flouted? Whose rule have I flouted by drawing this line? On's rule. Yes, I flouted On's rule and another person's rule. On's rule says singly false. No, I did not flout On's rule here. No. On's rule can only be flouted in degenerate orbitals. He says it enters into them singly first before pairing. For degenerate orbitals. So whose rule did I flout here? He said no two electrons can have the same number for all four quantum number. Have you forgotten? Pauli's exclusion principle. That no two electrons can have the same value for all four quantum number. If they have the same value for their principal quantum number, they have the same value for their azimuthal quantum number, they have the same value for their what's the next one? Magnetic quantum number, M sub L, they will have opposite spins. So these ones have similar spin. So this is a flouting of Pauli's exclusion principle. Did you not do quantum number? Do you still remember it? Should we take it in one shot after this, after organic chemistry? It's very simple, it's very short. We should take it. Okay. Alright, are you with me now? So now this is the way it's supposed to be written, right? Right? If Pauli's exclusion principle be obeyed. Now, what it does, the second thing it can do in its excited state, size carbon now, is that before, you know, okay, we have this and this here. Before, you know, it promoted this to this place, right? The same way to promote this again back to this place. But what it will now do is this. It will not hybridize the entire three with this one. It will hybridize only two of these guys with this guy. So we now have an hybridized orbital that looks like this. So you have your 2s1 hybridized together with 2px, hybridized together with 2py. Does this make sense? Then what you have is what? You have what? A 2pz that is what? Unhybridized. This guy is what? Unhybridized. These three are what? Hybridized. So the hybridization is occurring between what? 1s and 2p's. Is that okay? Does that make sense? So how many S character do we have here? 33.3% S character. Is that okay? And how many P character? 66.67% SP character. Does this make sense? This is in sp2 hybridization. And think of it, 1s, 2p, that's the meaning. Does that make sense now? Alright. Now, the other thing is this. This one, that is unhybridized will now form lateral overlap with another orbital that is unhybridized. Does that make sense? So this is the way carbon to carbon double bond is formed. So this carbon has sp2 hybridized. This one too has sp2 hybridized. So the 2pz of this carbon and the 2pz of this carbon will now do what? Overlap each other laterally. Is that okay? All right. So they overlap each other laterally. So that's why that bond can be broken because they still contain what? Unpaired electrons. Do you understand now? All right. So now, let's talk about the characteristics. So this guy, sp2 hybridized, is characteristic of who? The alkenes, the first unsaturated hydrocarbons. There are two sets of unsaturated hydrocarbons, right? The alkene and the alkynes. All right. What's it? Itunu. It's not a fault. If she had hair, she would not do that. Let's go, please. Alkenes, right? sp2 is characterized, is a major character of what? The alkenes. Of the what? Alkenes. Now, what kind of bond do we have? Now, there are two types of bonds that are formed here. They are double bonds. Okay, we said they form what? Single bonds. I'm sorry. So this one, they form what? Single bonds. But in this case, what bond do we form? Form double bond. Now, that double bond comprises of two types. They are what? The sigma, one pi. Do you understand? One sigma, one pi. So which one will be strongest? The sigma. Which one will be Which one will not be strong? The pi. Is that okay? Now the pi in this case has a bond length of about what? 134 nanometers. Is that okay? Okay. Now, are you with me now? Now. What is the, I can't remember the bond strength. I can't remember. But what is the shape? The shape, very, very compulsory. What's the angle between the bonds? Is what? 120 granotes. Is that okay? Because the shape that will be formed will be what? Trigonal planar. Is that okay? Or triangular planar. Trigon. Three sides, triangular. Is that okay? Triangular planar. Is that okay? Do you understand?
Yes, sir.
All right. And it is this kind of bond, the double bond, that permits for what? Geometric isomerism. So geometric isomerism can only be seen in what? Alkene. Somebody say alkanes. 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 All right. Now, so does it allow for free rotation? No. So there's no free rotation. Once you rotate the molecule, what have you formed? A different molecule. Do you understand now?
Yes, sir.
Once you rotate the molecule about that double bond, you rotate a molecule about the double bond. For example, we have a molecule like this. A molecule like this, C double bond C. You now have a particular R here, and you have a particular R prime here. The moment you rotate this one, such that it comes down, let's say the H here. Now, what form is this? The cis, is that okay? Or the Z, right? So the moment you rotate it, you rotate to one side like this. What will it become? It becomes the trans. So the transform, you rotate this one. The transform will have different property than this form. Do you understand?
Yes,
do you remember we said that the cis form usually has lower, which one has the lower boiling point? Cis or trans? No, I think it's the trans. The transform usually has lower boiling point than the transform. Is that okay? Is that okay?
Yes, sir.
Please check out that. Check that thing out. The one that usually has the lower boiling point. Is that okay?
Yes, sir.
All right. So now, so the molecule changes. So that's why we have geometric isomerism. Now, so it doesn't allow for free rotation. Then, what else do we have? What else? So basically, what that is saying is that thing that I drew for you just now, the bond angle between them is what? About 120 degrees. Okay. So that by the end of the day, when you add everything, you get your 360 degree about a fixed point. Does that make sense?
Yes, sir.
Okay. Now, the next type of isomerism is the SP isomerism. The next type of hybridization is what? SP hybridization. So in the SP hybridization, what do you think will happen? During promotion, after promotion, so this guy has promoted orbit electrons, right? So after promotion, who and who we now hybridize? 1s, we hybridize with what? 1p. Does that make sense?
Yes, sir.
So we'll have something like this. This is 2s1 and 2px. But these 2py1 and 2pz1, even after promotion, we know what? Hybridize. Are you getting it?
Yes,
they two will form what? Lateral overlap. Is that okay? So what we have is 1s and 1p. So how many percent s character? 50%, 50%. Do you understand?
Yes, sir.
Okay. So if that's the case, then what molecules are characteristic of this hybridization? The alkynes. Is that okay? Double unsaturated, right? Okay. Then so which ones are more unsaturated? Is it alkene or alkyne? Alkynes are more unsaturated. Okay. Now okay. So double bond here with what? How many bonds? Triple bond. Why? Because this one we hybridize another 2pz. This one we hybridize another 2py. Then this one will form sigma. Is that okay? So the bonds there are what?
Sigma.
1 sigma, 2 pi. Does that make sense?
Yes, sir.
Okay. Now what is the bond angle between them? 180 degree, right?
Yes.
180 granotes. So if it's 180 degree, what will be the shape? linear. Do you understand? Because angle on a straight line is what? 180 degrees. All right. Then what else do we have? Is there, that one does not even need rotation because, of course, the shape is linear. It forms a linear molecule. Are you with me?
Yes.
All right. Have we demystified hybridization?
Yes. Sir.
Is there anybody that don't understand anything? Eh?
No, sir. Nobody.
Okay. Okay. And the pi bonds there are actually shorter too. The pi bonds there are about 120 nanometers or 1.2 Armstrong. Yes, the sigma bond is still the strongest between the two. Do you understand?
Yes, sir.
When you break the first pi, it still remains one pi. Do you understand?
Yes.
So you break alkyne 1 pi, you go to alkene, raise your head.
Yes.
Then you break the second one, you now go to what? Alkane. Are you with me?
Yes, sir.
God will bless your father.
Amen.
All right, now let's go to fission of bonds. Is that okay? Fission of bonds, so that you know how bond breakage occurs. Is that okay? So you know what?
How bond breakage occurs.
All right, fission. Somebody say fission.
Fission.
Fission. All right. So first, bonds are held together. Those bonds you see, is that okay? They represent electrons that are shared covalently. Represent what?
Electrons that are shared covalently.
All right. So this is what the case is. Now, when non-metals want to bond together, what they do is that each of them will contribute a set of electrons that they both need. So if I need 2, I'll contribute 2 because I want to bond with someone else that needs 2. All right, is that okay? But in the case of, and it's the same for carbon too. Hydrogen needs 1. Carbon needs 1 from that hydrogen. So to contribute 1 for that hydrogen will contribute 1 for it. Is that okay?
Yes,
all right, now. But now, something happened in covalent bond. Fission occurs under certain conditions. Is that okay? And there are 2 types of fission that might occur. We have the homolytic fission. We have what?
Homolytic fission.
And the hetero. And the what?
Heterolytic fission.
Okay. Homo means what? Same. Is that okay? Lytic, splitting. Hetero,
Different.
lytic. Okay, so in homolytic fission or cleavage, that's another one. Is that okay? Do you remember we talked about cleavage? So cleavage too, bond cleavage. That's what we're talking about. Fission means bond cleavage. So now in homolytic fission, 2 substances that have the same, now they might be different guys. Is that okay? For example, Cl2 now. The bond between Cl2 is represented like this. Cl2 bond Cl2 or Cl and Cl like this. Is that okay?
Yes.
So each point here on this guy represents electrons. Is that okay?
Yes, sir.
So now this is what happens in homolytic fission. This is what happens with molecules that are equal, such as C and Cl. Homolytic fission is the most likely fission to occur. Is that okay? So what happens is that this guy will represent them by half arrowheads. This guy, once this bond breaks, 1 electron will come here. Is that okay? The other electron will come here. Is that okay? These are half arrowheads, half arrowhead. Does that make sense now? If I merge it, you see what I will get here. Does that make sense?
Yes, sir.
Okay. So once you see that the bond cleavage is homolytic, now homolytic fission or this type of fission usually form what we call free radicals. They usually form what? Free radicals. And that's what we'll see when we get to alkanes. We'll be discussing the concept of halogenation of alkanes. Halogenation of alkane is done by a free radical mechanism. Why? Because alkanes are non-reactive. So for them to react, you have to bring a free radical that is very reactive. Is that okay? So what happens is that each of these chlorine will now get a single bond, a single electron, a single electron, a single electron. So this makes them what? Extraordinarily reactive. Do you understand? So because of that, they can bring about a substitution reaction. They can bring about a what? Substitution reaction. Albeit also, in the presence of catalyst, homolytic fission can also occur between molecules of different compounds. A molecule of different elements. Is that okay? Homolytic fission can also occur. But the most likely to occur with same compound is what? Homolytic. Is that okay? And the most likely to occur under ordinary condition with molecules of different compounds is what? Heterolytic. So, and it is such that one of the molecule will have a higher pull on electron. Is that okay? And pull of electron is described as what? Electro. So, and using the Pauling scale, which one has higher electronegativity? Cl 3.5. Do you remember? We said fluorine has the highest, which is what? Exactly 4, right? This guy has electronegativity value of about 2.4. Carbon is about 2.5 or so. So you see it's very close to that of carbon, but very far away from chlorine. Is that okay? So on this scale, according to this scale, this guy has higher pull on electron. Is that okay? So when there's fission here, the most likely thing is that this guy is going to get both of the electrons to itself. So we have Cl double bond like this. I mean, single bond but 2 electrons. Do you understand now? Then this one will get no electrons, you just get a charge. So this one will get a formal negative charge. Are we clear?
Yes, sir.
Is it clear?
Yes, sir.
Good. Now, but I said homolytic fission can also occur here in the presence of the high temperature or UV, ultraviolet ray. Is that okay? Okay. Now, so that's heterolytic fission and homolytic fission. Basically, in heterolytic fission, we are talking about the unequal sharing of the electrons in the bond. While homolytic fission, we are talking about equal sharing of the electrons in the bond. Is that okay? Are you with me?
Yes, sir.
Okay. Now, that is all about the concept of fission. So we are going to see its application now. I mean, when we begin the reactions. Is that okay? Now, what are the possible things that cause chemical reaction to occur here? What are the things that cause chemical reactions to occur in organic compounds? Now, number one is, we call it the inductive effect. We call it what?
Inductive effect.
I've taught you this thing before, right? Or should we not talk about it? Let's not talk about it. No, don't worry. Nobody will ask you this in JAM. Let me just go on to another thing. We've talked about hybridization. We've talked about what again? We've talked about fission, okay? Yeah, because that is also necessary. So let's talk about what next. Let's talk about types of chemical reaction that you will see under organic compounds. Now, the first type of chemical reaction that you see is a substitution reaction. Is what? So substitution reactions are characteristic of not only, but mostly of what? Alkanes or what? Saturated hydrocarbons. Of alkanes or what? Saturated hydrocarbons. They undergo substitution reaction. What does substitution mean? You remove one and put another. Is that okay? Such as the one that I said we occur when, in methane, for example, with methane. So, for example, this methane here, CH4, if it wants to react with the chlorination of alkane, of methane, for example, or bromination of methane. So, let's use the bromination of methane. So, what happens first is this. What kind of fission will occur with this guy first? Homolytic fission. Is that okay? Now, when homolytic fission takes place here, we're going to have Br to Br. So you have homolytic fission will take place so that each of them share. So this reaction is initiated. There are 3 stages. You have the initiation stage. Do you remember? What's the next stage? IPT. Initiation, propagation, and what? Termination. Is that okay? In the initiation stage is when this guy, free radical mechanism is what initiates this reaction. Is that okay? So by the time it breaks, then you begin to see what bromination of this guy will occur it occurs in steps. Is that okay? And those steps are the propagation stages. Is that okay? So the first step that occurs is this. This guy is going to break the bond. You know there are 4 hydrogens attached to this guy. Wake that boy, please. There are 4 hydrogens attached to this guy. So we have Br to Br. Are you watching me? So one of these Br will break this bond. Are you with me? Because it's not a free radical. I hope you know that these guys cannot really react. Is that okay? But because this guy is a free radical, it has enough energy to break this bond and then attach itself to it. So it now forms 1, 2, 3. It has broke this bond away, and now this guy is attached to this guy. Then this guy will now attach itself to this guy plus HBr. Do you understand? Is this clear? So we now have methyl, bromo, methyl. Is that okay? Is it clear? Now the next stage, the next stage of this is BR will still be available in this thing. Is that okay? So in the next stage, another BR will abstract hydrogen from here again, and then BR will bond with it. Then it's now become what? 2-dibromo. It's now become what? Just dibromo, no 2, because do you understand? Because it's 1 carbon. So it's what? Dibromo methane. Do you understand? Do you understand what I'm saying? Are you sure?
Yes, sir.
On further reaction, it's going to become plus Br2 again. One we attach to it becomes Br to C to H to H to another Br. This becomes what? Dibromomethane. Is that okay? Dibromo what? Methane. If you probably don't know the name, maybe we should go to the name yet first. Is that okay? So you don't know the name? Do you know the name? So we have this and plus another HBr. Are you with me? And this process takes place in the presence of UV light. So what is the UV light doing here? To cause what? A free radical to be produced. Is that okay?
Yes, sir.
All right. So now the second type of chemical reaction that you see here is what we call an addition reaction. So what's the addition reaction? Now, what's an addition reaction? An addition reaction is one where an unsaturated hydrocarbon gets another atom added to the chain and it breaks the double bond. Is that okay? To remain a single bond there. So, for example, alkenes, unsaturated hydrocarbons, basically, they undergo what? Addition reaction. While saturated hydrocarbons, they undergo what? Substitution reaction. Are you with me?
Yes, sir.
So, for example, if I have ethene now, for example. Now, ethene is symmetrical. Is that okay? So, this is the case for ethene. So, if I want to add Br2, for example, bromination of this guy, what I will do is what? I'll just add Br to one of this side and Br to the other side. So, we have single bonds here. One of these bonds has been broken. Is that okay? By the time we break one of these bonds, there will be one electron on this guy, and they will use that electron to attach themselves to Br, this guy to Br. Does that make sense? And this one was formerly attached to 1, 2, 1, 2. Does this make sense? This one formerly attached to 1, 2. So 1, 2. Does this make sense? Therefore, we now have what? 1, 2, 1, 2, dibromo what? Ethane, right? Ethane, because it's what? Single bonds. We'll soon go over naming, so calm down if you don't understand what we are doing so far. But you got this, right? 2000. The major thing here is substitution reaction, saturated, addition reaction, unsaturated. What was this? So addition reaction is what? Unsaturated. Now, the other type of reaction that you might see is a replacement reaction or a displacement reaction. Is that okay? You might also see elimination reaction. You might also see what again? Those are the major ones. You might see elimination reaction. You might see replacement or displacement reaction. Okay? But in this case, don't worry. When we are writing the chemical reactions, I'll be telling you what kind of reaction it is. Is that okay? And because, of course, you already know what displacement reaction is, right? One thing that is more reactive will displace the other. Does that make sense? So, now let's go to isomerism. Is that okay? Before we go to isomerism, let's do naming. Is that okay? So that it will not, let's do naming so that, because when we start isomerism now, we still name. You get? And if you don't know how to name the guy itself, it doesn't make sense, right? Right? Yes, okay, so let's write naming of organic compounds. But master these two. So you are likely to be most commonly asked in JAM about addition and substitution reactions. All right, let's go now. Naming organic compounds. Now see, we're going to do a rule that covers for every organic compound. Is that okay? But in each case, we might be revising which rule, which name we want to give. Okay? So now, the rules. Let's write the rules. So when you want to name organic compound, the first thing you should know is this. the name, the prefixes, the what? Prefixes. So we have the first prefix. When you have one carbon, we have what? Meth. Two carbons, we have what? Abiodun, answer me. We have three carbons. Four carbons. Five carbons. You know that one day we'll get to paint. Six carbon. Six. Sixteen. Martin, seven carbons. Eight carbons. Nine carbons. Please, the rest of your answer. And 10 carbons, what? 11 carbons. Is that? 12 carbons. 13 carbon. 14 carbon. Tetradeck. Like that, like that. If we have up to 20, so it will go on like that. 20 will have what? Ikosa. Is that okay? Now, do you understand this now? So, you must first master all of this. 1 meth, 2 F, 3 probe, 4 boots. Everybody, let's go. 1 meth, 2 F. I don't pity you. Do you get me? If you don't still know it until now, since we've been doing it, raise your hand. Thank God. But at least you know the first thing. Hallelujah. 21. You know Ekosa. Is that okay? I don't know for you. In your jam, you will not be asked more than this 10. Is that okay? I'm just giving you the rest for no more. Is that okay? So now let's go to the naming now. Number. Okay. So since we already have the rule, I'll just no. There's another thing about functional groups. We did not do functional groups. We are supposed to talk about functional groups first. There's something about functional groups. What's that? Do you want to do functional groups? So functional groups, there's something about them. There's priority that is given to the functional group above the others. Is that okay? So the order of priority of functional group is this one. What functional group is this? Alkanoic acids. Before we do naming, let's go from functional groups. You can't, because we want to name all organic compounds, the rule that works for all. Is that okay? So now let's talk about functional groups. Now, what's the functional group, everybody? The functional group is what? Is that molecule or atom that does what? That describes the chemical properties of the molecule. Is that okay?
Yes, sir.
So it determines the chemical properties. That's the functional group. All right, now let's talk about the name and let's draw the structure. For example, if it's single bond, it's what? Alkane. If it's double bond, it's what? Alkene. It ends with in. That's basically okay. We should have the prefix and the suffix. Do you get it now? We should have the prefix and the suffix. So suffix, because if it ends the name. So this one doesn't have prefix, we just say "ein," right?
Yes.
For this one is what? "ene," right? Then triple bond. Ein, good. Then R group. How about R group? E, right? But you know it's not a separate family, I've told you, right? Alright. More like it doesn't really exist. It's just what is formed when we remove one hydrogen. Do you remember from alkane? Alright. Now, What if we now have the following? OH. What is this? Good. Alkane all, right? But what if it appears as a substituent? Hydroxyl. Is that okay?
Yes, sir.
Now, how about this guy? C double bond O H. That is terminal. What would that be?
Now.
Alkanal. Good. That's the suffix. What's the prefix? The prefix. If it was not the only function, if it has a senior brother there, that's a higher functional group. What would that be? What would it be? Oxo. God bless you. Do you understand?
Yes, sir.
Oxo. Why? Because this carbon is going to be a part of a chain. Does that make sense? And okay, yeah. So we get that, right? So what if it was R C double bond C double bond O and R? So that this, we call these two what kind of compounds? Carbonyl compounds. Is that okay?
Yes.
What do I call them? Carbonyl compounds. So this guy, the prefix will also be what? Oxo. Does that make sense? Oxo groups. Then this thing was the suffix. What family is this? Alkanone. Good. Own. Is it clear?
Yes, sir.
Okay. Then what again? What again? So which other group? How about this? NH2 groups. Amine. So in the prefix what? Amino, right?
Yes.
Then amine in the suffix. Does that make sense now? Then yes. So if you have a molecule where there exists this guy and this guy, the priority will be given to what? This guy. Does that make sense now?
Yes.
Over this guy. So where there exists this guy and this guy, priority will be given to this guy over this guy. This guy and this guy exists in the molecule. This guy will take the parent name. Does that make sense now?
Yes.
That's what we mean by priority. Okay. Then what if we had this guy now? What if we had C double bond O H? What would this be? Does this guy have prefix? No, because it cannot exist as a substituent, right? So it means that it's what? Oic acid. Is that okay? So the group is called carboxylic acids. Are you with me? Oic acid, thank you. Are you with me now? So primarily you are going to be tested. Okay, there's another one. How about this guy? RCROR. What group is this? Alkanoate. Ethers. Ethers. Is that okay? So it's also an oxo group. Is that okay? Or epoxy. That's their family name. Epoxies. Is that okay? Is it clear?
Yes, sir.
All right. How about we have C double bond O and OR like this. Esther, thank you. Is that okay?
Yes.
Do we understand?
Yes, sir.
Okay. So that's primarily what we have. So we are good now for functional groups, right? But wait. Now, usually we don't have molecules that have this guy and all these guys together. Is that okay? They are a separate group. Is that okay? But this is the order for the naming that we're going to be doing. This is the order that we'll follow. Do we understand now? Okay, so now let's write naming organic compounds now. Yes? Alkanoids. This is an alkanoid now. Esther. This is not alkanoid. This is alkanoids now. Don't you know Esther? Okay. So now naming organic compounds now. Now you know how to name organic compounds. The first thing you must do is what? To identify what?
Longest carbon to carbon chain.
Longest carbon to carbon chain. That will be the what? The parent chain. It will be the what?
Chain.
Naming of some here change. Oh, is that okay? We've done that before, right? They are naming the way we name them changes in a way. All right. That's number one. Number two, what do? Identify position of what? Position of substituent or first functional groups. Is that okay?
Yes.
Is it that you identify position of substituent or functional groups? Is that okay? Now, where there are substituent and functional groups, first, what are substituents? Substituents are any group that is attached to carbon that is non-hydrogen. Any group that is attached to carbon that is non-hydrogen is what? A substituent. So, if it is chlorine, it will be a halo group, right? If it is this one, oxygen, oxo, right? If it's sulfur, what would that be?
Sulfide.
Yeah, so is that sulfide? Do you know okay, there is SH, this thiol. Is that okay? So just depending on any this thing you have there, any guy that you have on that chain, those will be substituents. Is that okay? And if they are the one, if it's any of this family, they will be what? Functional groups. Are you with me? Now, then there is so when you identify the position, you will now number the position, number those guys, number the carbon to carbons that you have counted, number it in such a way that it will give the substituent or where it is functional group, the functional group. Functional group takes priority over substituent. Is that okay? So where there is a functional group and there is a substituent, you will number in such a way that will give the functional group the lowest possible number. Number the functional group is on. Number the functional group, give the functional group the lowest number. Is that okay? And if it's only substituent, give the substituent the lowest possible number. Okay. Now, sometimes also there might be more than one substituent. If there are more than one substituent, you now use what?
Die.
You now use prefixes like di. What do we call these prefixes? I've forgotten them. You use prefixes like di, tri, tetra for 4, right? So if, for example, chlorine occurs twice, to what? If chlorine occurs on carbon 1 and carbon 5, that would what? 1, 5. Does that make sense now? 1, 5 dichloro. If it occurs twice, 1, 5, 3 trichloro. And notice, you must write the position of that substituent together with this before you write this. Does that make sense? So now, when there are more than one substituent like that, when you want to write the numbers, separate numbers with what? Commas. Separate numbers with commas. And between number and letter is what? Hyphen. Hyphen. Exactly. And the last thing you will now consider also is alphabetical order. Okay, good. Now also in this case, there's also alphabetism. The way you will now write your name should be such that the one with that has you write it in alphabetical order. That's my point. So for example, if you have dibromo and chloro, which one will come first? Chloro, whether it's 5 chloro and 2,1 dibromo, it will what? 5 chloro, 2 dibromo. And now that let's apply these 3 rules quickly on that. If you have chlorine on 5, that will be 5 chloro dash. So you see that between number and letter, I put a dash, right? And between number and number, I'm an hyphen, thank you. But between number and number, I'll put a comma. So you see, for example, 1 and 2, 1, 2, dibromo. Now, yes, thank you. Now you see that, so we apply the first rule. It says that we should double this because occurring twice. So we have di. So the numbers on which occur are 1 and 2. We don't number numerically. We don't arrange numerically. We arrange in alphabetical order. That's why 5 is coming for 1 and 2. Because 5 is the number for chlorine. So C comes before D. Does that make sense? Okay. I hope we are good now. Can we go on to naming? Pause it. Let me look for some name. Oh, no. Okay. So let's name these compounds with the rules that we have mentioned or discussed so far. We are going to name others, another 5, But I want you to first see how to name directly first. Is that okay? Because when we begin to put some kind of irregular kinking in the chain, you will see that it's not as straightforward as this. Is that okay? But let's name these straightforward ones. And I want you to stick with me. It's very simple. So the first thing says that count the carbon to carbon chain that is the longest, right? In this case, this is not carbon. No, don't mistake it for carbon. So this is carbon to carbon to carbon to carbon. So the longest one here is what? 4 chain. Is that okay? Yeah. So you already know that there's going to be what? A boot in your family name. Do you understand? Or your parent's name. Do you understand here? So this parent name here is going to contain boots. That's the meaning. And if you look at it well, it's single bonds all through, right? So there's going to be something like butane at the end. You see what I just did? I've written my butane already. Now the first thing to now do is, okay, we've written this. So even though you don't write this, even though you don't write this, but let's say as I've written this now, identify the constituents or functional group. The functional group here is A. Is that okay? So substituents attached here. How many substituents are attached here? 1, 2, 3. Now we have 2 directions that we can number. Is that we number in this direction? If we number in this direction, we have 1, 2, 3, 4. Is that okay? In this direction, chlorine, the 2 chlorines we have numbers 1 and number 2. Bromine will get number 3. If we number in this direction, bromine will get number 2. This one will get number 3, number 4. So our 2 combos are 1, 2, 3, or 3, or 2, 3, 4. Which one is the lowest possible number? 1, 2, 3, right? So we are using this direction for our numbering. So chlorine, so the 2 substituents here are chloro group and bromo group. Does that make sense? Yes, so chloro appears twice. So we'll say 1, 2, di, chloro. Is that okay? Yes. Chloro. And what? 3, bromo. You see, between number and number, let me write it so that you follow along. Chlorine appears on 1 and 2, right? So we say 1, 2. Then chlorine is twice. Di, so you put a dash, di, chloro. Are you with me? Bromine is number 3. Bromo is number 3. So 3 dash bromo. Is that okay? So how do we now arrange our name? So looking at this, which one should come first? Bromo or dichloro? Bromo. So it should be what? The name will be 3 bromo, 1, 2 dichlorobutane. But because of 4 carbons. Aim because of single bonds all through. Does that make sense? All right. Who did not get this one? All right. So let's go now. The longest carbon to carbon chain in this next one is what? 1, 2, 3, 4, 5. 5 carbons, yeah? Yes. So we have what? Pent. Does that make sense? Yes. Now, looking at this, there's a double bond here, right? Yes. So the double bond is going to take the priority because it's a functional group. Is that okay? So what do we get now? First, let's identify the other substituents. Substituents are on what? This carbon and this carbon. Let's see which direction. Now, the direction that I go to number now, is it the direction that will give this substituent lowest number or give this functional group lowest number? The functional group. If we number in this direction, this functional group will be on carbon 1, 2, 3. Is that okay? If we come from here to be on carbon 1, 2, so we'll use this numbering. Is that okay? Yes. Now the bond is always the bond that a carbon carries is the one in front of it. Is that okay? Yes. If we come from here, this will be the front. Is that okay? So we have carbon 1, carbon 2 is bearing this double bond. So we'll be using 2, we'll be using this direction. Is that okay? Yes. So then the substituent will take the number that is already apportioned to them because of the position of this functional group. They are not our priorities. Is that okay? Yes. Okay. So they will get, this one will get 1 by virtue of numbering from here. Is that okay? And this one will get what? 3. And if you look at it for yourself, is this direction that will still give them the lowest possible number? Does that make sense? Yes. Good. So we now have chlorine is number 3, chloro is number 1 and 3. So we always write the substituent first, right? Always write what? Substituent first before the parent name, isn't it? Yeah. So we have what? 1, comma, 3, dichloro, paint now, wait, because of 5 carbons. Now there's a double bond here, right? So the double bond is on carbon 2. So we'll say paint 2 in. Does this make sense? Or 1,3-dichloro-2 pentene. Does that make sense? you understand that method? But if you don't understand that method, you got this one, right? At least. Did you get this one? You. Did you get it? What did you not get there? The number one. Did you get number two? Did you get number one? Okay. And which one? What did you not get there? What is this? And you said you didn't get this one. This one. Okay, you got it. Good. So we have 1,3-dichloropentene. Good. Now check the memory storage. Remaining. Oh. Okay. So from here, now we have 2 double bonds here, right? So double bond is again our functional group. Is that okay? Double bond is again our functional group. So we're going to have here double bond. Our substituents, this and this. Is that okay? These 2 guys are our substituents. Now, if you go over that, then we're going to have, since these 2 guys are substituents, our functional group are double bonds. If we number in this direction, our double bonds will fall on 1 and 3. It will come from here to fall on larger numbers. So we are going in this direction. Choose the direction that gives that double bond the lowest number. So this direction gives it the lowest number. So if we go like this, we will have 1 and 3. That's where our double bond is, right? And because the double bond appears twice, it's what? Diene. Does that make sense?
Yes, sir.
So it means that at the end of the day, we are going to have 1,3 diene. Do you believe with me? Okay. Now, what are the substituents attached? Iodo, right? Iodo is on carbon from here. Iodo is on carbon 3 and 4. So what do we have? We have 3,4 diiodo. Does that make sense? Diiodo. 1, 3. Oh, sorry. Diiodo. Now, how many carbons do we have here? Sorry. 6 carbon, right? So that becomes what? Hex. 6 carbon. Hex. 1, 3 diene. Does that make sense?
Yes, sir.
Is it clear?
Yes,
okay. Then the next one here. I told you it should not be as sweet as this, so that everything will be on straight line all the time. It's not always like that. Okay. So for this case, for example, we have C. How many C's do we have? 5, right?
Yeah.
Okay. Now where are our substituents? Where is the functional group? The last guy, right? Anywhere you see COH is going to take the priority. Is that okay? All right. But we are going to count this carbon as part of it. Do you understand? So now our substituent becomes this guy, and this guy. Any other group that is not H there becomes the substituent. So how do we name this guy? Let me clean these ones. That memory is not on our side again. That memory. So our substituent now become chloro, oxo, and bromo. Which one comes first? Because they appear singly. Bromo should come first, right? And which direction are we following? This direction, right? Because this one takes priority. So the only direction that gives it the lowest number is this direction. Is that okay? So come here. Bromo takes 2. So that becomes 2 bromo. Are you with me?
Yes, sir.
Then you go like this. Between oxo and chloro, which one comes first? Chloro, right? So it's on 5, right? 5 chloro. I'm putting a dash because, okay. The next one is what? 4 oxo. Are you with me?
Yes, sir.
How many guys? Pent, right? And single bonds all through. Tanoic acid. Does this make sense?
Yes, sir.
All right. Then the last one. We have this guy. We have Al. And we have C double bond over here. And we have C double bond over here. Is that okay? Which one takes priority between, what functional group is this? What alkane, right? What function aldehyde? What functional group is this? Alkanone. Is that okay? Which one takes priority? Own. Does that make sense? So this name will become what? There is a substituent here, right? So we are going in which direction? This direction. How many carbons have we here? 1, 2, 3, 4, 5, right? So that becomes 5 chloro. Now, 1. No. Yes, 1 oxo. God bless you. 5 chloro. 1 oxo. God bless you. 1 oxo because of this guy, right? This guy takes priority. Is that okay? 1 oxo pent and 2 own. Does this make sense?
Yes, sir.
We did not get it, raise your hand. We said 5 chloro because of that guy. We are taking this direction, not that direction, because there's a functional group. And this functional group here, the functional group we are considering is the own group because it takes priority over the alkanal. Does that make sense? Then we now have 1 oxo because there's aldehyde group here, oxo group here. It's supposed to be aldehyde if there was no this guy. Does that make sense? Okay. Should we take one more? Okay, let's name this thing for me. Let's name this thing together. Let's see who will be faster than me. I'm going to draw it and you name immediately. Is that okay? Who's done? What's it? Okay, so to name this guy, yes, I already cleaned this H. Now, to name this guy, now, once we see a double bond there, we know that there's a functional group, which is double bond. So which direction are we going to take? We're going to take this direction now. Now, this one is not so sweet because it's not straight. So what direction gives us the lowest the high, not first the lowest possible number, the direction that has the longest carbon to carbon. So if you look at this, there are 3 carbons squeezed together inside this thing. Is that okay? So this is 1, 2, 3, 4, 5, 6, 7, 8. Does that make sense? Yeah. If you're going to take 1, 2, 3, 4, 5, 6, you'll be wrong. Is that okay? So this is, there are 8 carbons here. 8 carbons correspond to what? Oct. Okay, so which direction are we going to take? Is it this direction or this direction? Because there's a double bond there, we're going to take this direction. So we have 1, 2. Okay, and there's a substituent. How many substituents do we have here? 2. This is a substituent. This guy becomes a substituent because it's no longer part of the parent chain. All right. So since it's no longer part of the parent chain, it becomes a substituent. And the first substituent we'll find on what? Carbon 2. So that will be 2 chloro. For now, don't order. First get what the substituent out. The next guy, 1, 3, 4, 5. 5 methyl. Does that make sense? Okay. Those are all the substituents here, right? Let's now name 1, 2, 3, 4, 5, 6, 7, 8. So that will be oct. 2 in. Does this make sense? So our name now becomes what? 2 chloro 5 methyl oct 2 in. Why are you not doing like it was hard? No, now when we were starting the naming, you were first looking like. Do we get it? All right, should we go? Let's go to isomerism. So I hope the subject of naming has become clear. Okay. Now, the word isomerism is gotten from 2 words, which are, pause please. So we said isomerism. Isomerism is gotten from 2 words. We have iso, which means what? Iso, equal or same, right? Okay. And mer, what does it mean? Unit, right? Unit. So we say that isomerism refers to the occurrence of the definition requirements in your textbook is that 2 or more molecules that have the same molecular formula but different what? Structural formulas, okay? So that's isomerism. They have the same molecular formula, but different functional and structural formula. But basically, isomerism is split into two groups. We have the what? The structural isomerism and the stereo isomerism. Are you with me? Now, in the structural isomerism, we are going to be looking at the straight chain isomerism, the what? We are going to be looking at number 2, the positional isomerism, the chain cycle isomerism. Which one again? Tautomerism and metamerism, right? You remember metamerism? We discussed it, right? Okay. Then under stereoisomerism, we're going to see geometric isomerism and what? Optical isomerism. Are we clear? All right, let's quickly look at them all together. So for straight chain isomerism simply means when there is difference in, it's still the same structure, they have this different structure but the same molecular formula. But in this case, because of there is a kink in the chain, the structure, the name becomes different. For example, look at this structure. The typical one we draw is butane, for example. Butane, which is the simplest one. We have this guy. Butane is, how many carbons do you see here? 4. So we have 1, 2, 3, 4 like this. Now this guy, if I decide to bring this methyl group out of this chain and come and put it somewhere, look at what we'll get. 1, 2, 3. I change the position. I come and put it here in the middle. Now if now what does this become? This was what? Butane. Does this make sense? This is butane. Now the moment I remove this, I break the chain and come and put it here. What happens? So there's a kink here. So is either we have propane, either ways. Do you understand? But there is now one will now become a substituent, because if you take this as propane, this becomes what? Substituent. That becomes what? 2-methyl propane. But we said isomerism in this case they have what? The same functional molecular formula. So let's see molecular formula of this guy. 1, 2, 3, 4. C4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. AH10, right? Let's see how many H's this guy, how many C's this guy have. Still 4, C4, H1, 2, 3, 4, 5, 6, 7, 8, 9, 10. AH10. You see? The same molecular formula for different what? Structures. Is that okay? This one we just kinked the chain. That's why it's called straight chain isomerism. Are you with me? Now the second one is positional isomerism. So for butane, how many isomers does it have? 2 isomers. Itself, N-butane and methyl propane. Is that okay? Propane does not have any isomer. Is that clear? Because there's no amount of kinking you can do. You keep adding to the terminal carbon. Do you understand what I'm saying now? All right. So, and that's the lowest guy that has the lowest isomer. Now, okay, one thing with isomerism with that kind of isomerism is that the more the kink, what happens to the boiling point? The lower the boiling point. Do you understand now? So it means that butane will boil at a higher, we have a higher boiling point than what? 2-methyl propane. Is that clear? Right. Now for positional isomerism, positional isomerism is like that one too. For example, but it has to be with a group that can be distributed around. For example, look at this now. In positional isomerism, what group is this? What group is this? What group am I drawing now? What family is this? Alkane, right? Now, what is the name of this guy? This will become what? 1, 2, 3, 4, 5. That what? Pentan 3 all. Does this make sense? OH is all, right? Okay. And because of single bond, or this is the way we named it. 1, 2, 3, 4, 5. Pent, single bond, and position of functional group 3. Then functional group family all. Does that make sense? So pentan 3 all. Now let's change the position of this guy to become all right. We have changed the position of this guy to this side. Does that make sense? So what do we have here? Pentan what? 2 all. Does this make sense? Why is it pentan 2 all? Because now on carbon 2. Are they the same? No. But how many carbons do we have? 5 carbons. How many H's do we have? 10 H's. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 rather. 12 H's. How many carbons do we have here? 1, 2, 3, 4, 5. 5 carbons. How many H's? 12 H's. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Do you understand? So yes, we'll count it now. Do you understand now? So, and if you don't want to count it, it means you are writing the functional group as the molecular formula as C5H11OH. This one will be C5H11OH. Does that make sense? Eh? Hungry? No, those are now the isomers. We could bring it to the first one to become what? Pentan all. Do you understand now? We bring it to the first carbon, pentan all. But the only ones that we have. So in that case, what kind of isomers can we have? Pentan 3 all. Oh, Pentan. Yeah. We can also move the methyl group. Is that okay? So the isomer of that guy will be very much. Is that okay? Because we can move the methyl group. We can move methyl groups. 2 methyl groups. We can move them. Do you get it? We can move the first methyl group twice. We can move 2 methyl group once. Then we'll now move the OH group again like 5 times. So that is about 10 isomers. Do you see that? All right. So now chain cycle isomerism is just isomerism that occur between a straight chain hydrocarbon and a cyclical hydrocarbon. The idea is this: a cyclical alkane has the same number of is an isomer of its corresponding alkene. A cyclical alkane is an isomer of what? Its corresponding alkene. As in, for example, if I have this is a cyclical alkane. For example, what's this guy? If I have this, what's this? Propane, right? Now, what if I have this? What's this? Cyclopropane. Because remember that 4 bonds must be around carbon. So here, 1, 2, 3, 4 for this guy. Here, 1, 2, 3, 4 for this guy. Does that make sense? Okay. So how many carbons are here? C3. How many H's? H8. Does this make sense? In this case, it was what? C3. No, this is H6 now. 1, 2, 3, 4, 5, 6. In this case, it was C3H8. You see that they are different. But if we now take C, double bond C and C here, we now take here, we have H, here H, here H, here H, H, H. How many H's do we have? 1, 2, 3, 4, 5, 6. So C3H6. So what do you see? That a corresponding alkene we have this will be an isomer of an alkane or of a cycloalkane. Does that make sense now? This is called cyclopropane. Is that okay? And this will be called what? Propane. Does this make sense? The same way with butene. So cyclobutene we have the same, will be an isomer of what? Cyclobutane rather will be an isomer of what? Butene. God bless you. So what if it was cyclobutene? Butane. Do you understand now? Should I prove that to you? Should I show you? Watch it. Look at it. 1, 2. I could put it anywhere. I could put the double one anywhere. So around this guy, we already have 1, 2, 3 bonds. Are you with me? Here around this guy, I already have 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay. So this is already C4. H 1, 2, 3, 4, 5, 6. 6, right? And we call it cyclobutene. Is that okay? Position of double bond is where we start counting from. So cyclobutene. Now, how about 1, 2, 3, 4? Triple bond here. This becomes H here. Here H, here H, here H, here H, here H. Let's see. C 1, 2, 3, 4. H 1, 2, 3, 4, 5, 6. H6. You see they are equal now? So, and this is what? Butane. Do you understand now? So that is chain cycle. Storage. You cleaned everything now. Cycle did what? Chain cycle, right? What's the next one? Metamerism, right? Now metamerism is when there are 2 functional groups, that 2 different functional groups that are metamers. We call them what? Metamers. They have the same basic molecular formula. Is that okay? For example, it's usually between ethoxys, ethers, that's ethers. Is that okay? And ethanol and alcohol. Is that okay? Is that okay? And alkanols. Are you with me? So ethers, for example, no, it's frustrating. Is that okay? So we have CH3 to O to CH3. Should be written like this. So what is this guy? This is methoxymethane. Yeah? So what's the basic molecular formula? C2H6O. Let's look at alcohol, ethanol basically. Ethanol is like this. OH, H, 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 H. That's C2, H, 1, 2, 3, 4, 5, 6, H6, and O. Do they not look alike? So they are called what? Metamers. They have different functional groups. Is it clear? Are you sure? So they have different functional groups. This one is oxo, and this one is what? Alcohol. You understand here? Yeah? Okay, so they are metamers. Then the last type of functional group is tautomerism. This one exists when there is dynamic equilibrium between two types of functional groups too. It's usually between, we call it the keto-enol tautomerism. We call it what? Keto-enol, that is keto group and enol group. So for example, if we have C double bond O here, and CH3, let's say CH3 here, for example. This form here can revert. What's it? So now tautomerism is when there is a dynamic equilibrium between two forms of a compound. No, it's not the same compound, but two functional groups actually. So this guy can revert its form to, there's dynamic equilibrium, do you remember? Between, this is what? Pentanone, right? We can also form, look at this guy now, look at this guy. We can also form this guy. You know, it's keto-enol. So this is the keto group, right?
Yes.
Okay. Then this guy can become C double bond, C, now we have OH and CH2. So what happened? This guy abstracted his resonance structure. Let me show you the resonance structure. It's very simple. This guy abstracted the double bond and became slight negatively charged. Then the H reacted with it, and then, or basically this way we say it. We say that this thing falls here, double bond falls here. Is that okay? But basically what this guy did is that it abstracted the double bond to itself, and then it formed bond with this guy. Is that okay? Then this guy now became a carbo. Will it become a carbocation or carbanion? Carbocation, right? Are you sure?
Yes, sir.
If this guy takes minus, okay, carbocation, good. So do you understand now? Alright, so but when there's dynamic equilibrium, that's tautomerism. Now after isomerism, what are we supposed to do? Alkane, right? Right? Okay, let's quickly go over it. And we've done it before, as in alkane. Now the alkanes now. So the alkane have the general formula. Okay. So it means that when n is 1, what are we going to form? Methane, right?
Yes, sir.
Because if n is 1, we have CH4 at the end of the day. N is 1, C1 into bracket, H into bracket 2 into bracket 1 plus 2. This becomes 2 times 1, 2 plus 2, 4. So CH4. Does that make sense?
Yes, sir.
Alright, so then the homologous series is a series in which each successive member differ by a CH2. Is that okay? Yes, each successive member differ by a CH2. Let me prove that to you. The next member here is what? Ethane, right?
Yes.
What's the formula of ethane? C2H6. Now, if you look at it, the difference between them is 1C and H2. If I add 1C and H2 to this guy to form this guy, isn't it?
Yes, sir.
And if we go down like that, down the group like that, each successive member differ by what? CH2. So each successive member is called a homolog. This is a homolog, this is a homolog. We call it homologous series. We say homologous series is where each successive member differ by CH2 or differ by 14 grams in molecular formula. Is that okay now?
Okay, sir.
Okay. In molar mass. Now, another thing about them is that as you go down the group, the characteristics of the thing too become expanded. For example, in the first series of alkane, the first 4, they are what? Gases. Then the next 8 group or 13 groups are what? Liquids. Then the next one, fixed solids. Do you understand now?
Yes, sir.
So that is the way the gradation as you go down the group. So that's how we form homologous series. Now, there's something about types of formula. We have molecular formula, we have condensed formula. Do you ever ask that? No. No, right? So let's not treat it. Okay. Now with alkanes, let's talk about how they prepare them in the laboratory. But basically, we are going to the classical example, the classical member that we'll be talking about is what? The methane. Is that okay? Now, alkanes first are generally called what? Paraffins. From the word param and what? Affinis, right? What does param means? Weak. What is this? Love, affinity, right? So it means they are weakly reactive. Paraffins, weakly reactive. So for them to actually react, they need catalysts, just any form of, they need catalysts. For example, in the substitution reaction we're going to be seeing just now, you will notice that the UV light is what creates a free radical mechanism. Do you understand now? So that is for them because of they are weakly reactive. All right. They cannot undergo addition reaction. Now, what is methane? Methane is commonly called what? Marsh. It's commonly called what? And we said is the main cause of fire damp in coal mines, right?
Yes.
No, it's called fire damp in coal mines, but it's the main cause of explosion in coal mines. So we call it fire damp. Is that okay?
Yes,
Commonly called marsh gas, methane itself, and is what? This guy. So, and natural gas contains this methane, 95%. Is that okay? Natural gas. So we basically use it as fuels. Is that okay? In fact, the main constituent of our of our cooking gas is majorly methane, butane, and something, right? Methane, butane, and what? I can't remember. But this guy is the chief component. Is that okay?
Yes, sir.
Okay. Now, how do we prepare them laboratorily? In the laboratory, there are different methods. Now, the first method that we discussed, do you remember, is the... there are many methods. Which one is coming to your mind? Okay, let's talk about the method that we have. We have the words reaction. The words reaction. Which other one? We have the words reaction. We have the halogenation, right? Catalytic halogenation. Is it halogenation or hydrogenation? Hydrogenation of what? Alkenes. Is that okay?
Yes, sir.
What did I call this guy for us? Okay, don't worry. I mentioned it this afternoon, don't worry. But just get it. The idea is for you to get it. Nobody will ask you to name it in JAM. So catalytic hydrogenation, we also have coal-based process. Then we have the Grignard reagent. Do you remember? Grignard reagent. What is the formula for Grignard reagent? RMGX. Do you remember? Master this. So RMGX is what? Grignard reagent. Is that okay? So hydrolysis of is Grignard reagent. Any methyl group, alkyl group rather, any alkyl group, Mg and halide. X is the symbol for halide in organic chemistry. Is that okay? Any halogen, fluorine, chlorine, bromine. But we usually use the weakly reactive ones for most of our reactions. Is that okay? Because of the degree of reactivity of fluorine and chlorine. So we use bromine, iodine most of the time. All right, so Grignard reagents, which other reaction? So let's talk about the decarboxylation. Do you remember now? Decarboxylation using, in fact, in your chemistry, do you remember, is decarboxylation that was discussed? Decarboxylation of ethanoate, sodium ethanoate. Let's start with that, sodium ethanoate. So what's sodium ethanoate? CH3CONA. What do we use to decarboxylate it? We use what? NaOH. Is that okay? Now, so, and the NaOH we call it quicklime that has been slaked, right?
Yes.
Quicklime that has been slaked with NaOH. And the reason is because if it's slaked, quicklime alone attacks glass. Do you remember? Do you remember? So, and we also mentioned something about, okay, so quicklime that has been slaked, so with NaOH. So by the time you react it, you're going to get C, in this case, you're going to get what? Ethane, isn't it? Is that not what you get? You get ethane and, no, you not get ethane, you get methane. Why? because this guy will form CO3. So we'll get CH4 plus Na2CO3. Na2, does this make sense? CO, you see the way I'm getting it, right? CO3, then CH3 plus H, CH4. Does that make sense? So if I want to if I want to get ethane, what will I use? Sodium propanoate plus what? Plus NaOH. Is that okay? Remember I said it's quicklime that is slaked to this. So this is CaOH plus NaOH. Do you understand? But the active part is this guy. Do you understand? So that's why we're writing it this way. Does that make sense to us? Is it clear? Alright. So that is for decarboxylation. So it has been decarboxylated. That's what? Decarboxylation. Another decarboxylation that takes place is in coal-based process. Now, in what reaction? We basically use sodium. What reaction is like this? We have a particular haloalkane. Is that okay? Haloalkane. So we have two haloalkane. This is methyl group plus halide plus sodium. Is that okay? It will give us, by the time you do that, it's going to give us RR and NaX. Na2NaX. So by the time you do this, so this guy is used to synthesize symmetrical alkane. It's used to synthesize what? What are symmetrical alkanes? For example, is this guy symmetrical? Is this guy symmetrical? Is this guy symmetrical? Is this guy symmetrical? Is this symmetrical? It is symmetrical if we can split it into two equal parts. Is that okay? This guy can split into CH3, symmetrical. Cannot be split. If we split this guy, we'll get CH3, C2H5. So non-symmetrical. This guy can split into C2H3, C2H5, symmetrical. Is that okay? Yes, so it means that the reagents we are going to use here is going to be what? One that has two components that want to merge together. Is that okay? Yes. So that's in Ward's reaction. So we don't need to write chemical reaction now, do we? Okay. So the next is catalytic hydrogenation. We are going to be talking about that a lot. So remember the catalysts. The catalysts are what? Either what? Palladium or what? Platinum or what? Do we use nickel? Do we use nickel? Yes, we use nickel too. Because I remember that nickel is the only one we use in fat hydrolysis. Is that okay? All right, hydrogenation of oil. Are you with me? Don't forget those, those guys, vanadium. Vanadium is used in vanadium 5 oxide or just vanadium? Vanadium? No, we don't use vanadium. We don't use vanadium. Do we know? We don't, right? We use finely divided ion in neighbor process. I want to remember organic reactions that we use catalysts. They are much now. When we get there, we'll treat them. Are you remembering? Okay, let's just go. Let's go. So we have catalytic hydrogenation. Simply means we hydrogenate an alkene. For example, let's hydrogenate ethene now. What's this guy? Ethene, right? By the time we hydrogenate it, what will happen? Very simply, this guy means H plus H. Let me write a reaction with this so that some people will not say, we didn't write it, so I don't understand it. This bond will cleave. Once the bond cleaves, it's going to produce, C was bonded to two guys before. One of these hydrogen will come to it, becomes H, and with the two that was bonded to go. Now this bond has broken, one of the bonds has broken, then two hydrogens were attached to this guy before, then the third hydrogen will come from here, and then we have what? Ethane. We have what? Ethane. Do you understand? Is this clear? Another way is synthesized is pyrolysis. Do you remember? Pyrolysis. When what? What is pyrolysis? Another name for what? For cracking. Cracking, right? Do you remember cracking? It's also called what? Pyrolysis. Do you remember what is fire? Fire. Lysis, right? So when you heat up petroleum at a very high temperature, as high as 500 degrees Celsius, 450 to 500. Is it Celsius we use or Kelvin? Celsius. So you will get a pyrolysis will happen. That is, the molecule will break down into many components, and alkanes are more likely to be formed. Many alkanes are formed. Is that okay? That is pyrolysis. Then for Grignard reagents, it's just hydrolysis of Grignard reagent. I said I was going to write the formula here. So for example, it will be symmetrical. So let's use CH3Cl. Is that okay? 2 of CH3Cl plus 2 sodium metal. And what do we have? We are going to get at the end of the day NaCl twice, right? Plus CH3CH3. CH3CH3. What's that? Ethane. Do you understand now? Is this clear at all? Who is confused? Nobody. Right. Let's go to Grignard reagents. Now, with Grignard reagents, when you hydrolyze Grignard reagents, so for example, I could use CH3 there. If I use CH3 here, MgX plus H2O. So what do we get here? We are going to get, our end product is going to be MgOH plus that halide. So let's use Br here. Is that okay? This is what we always end up getting. Is that okay? MgOH plus that halide. Is that okay? Then, so in this case, if we remove this guy, and this guy is HOH, right? Are you with me?
Yes, sir.
This guy and this guy has gone. So what do we have left? What are we going to form?
Yes, sir.
Who is lost? If you don't understand, raise your hand. Should I use another one to explain? Should I use another example? Or you understand this? Just know that you first remove this MgOH and bring out your water. Hydrolysis of this guy. Bring out your water. Water is HOH. Remove OH and put it here, and the Br that is here. The MgBr that is here. Then what you have here plus H is what you form. Does that make sense? So this one can be used to synthesize asymmetrical. This one asymmetrical. This one asymmetrical. But that one, Ward's reaction is for synthesizing what? Symmetrical alone. Is that okay now? All right. Let's now talk about the reactions that alkanes undergo. The reactions they undergo. The first reaction is called what? Substitution reaction. Let's talk about their combustion first. The combustion reaction. Combustion. What does combustion mean? Reaction with oxygen or burning, isn't it? When you hear combustion, is burning. So now, in combustion reaction, our methane, which is what we're using, is going to react. Now, in the presence of excess oxygen, what will it produce? Produce CO2 plus what? H2O. You balance the reaction yourself. But we're supposed to know the formula offhand. I told you guys to cram it the last time. What will be here? 2. No, the formula y over 4y plus. I'm coming before we go there. So this is in excess oxygen. In insufficient supply of oxygen, what do we form? CH4 plus O2 form what? Carbon and what? H2. Do you understand now? So by the time you write the chemical, you balance it. Let's try to remember this now. So if this one is X, so if it's CX, HY, for this place, for oxygen, it's what? X plus Y over 4. O2 to give, or Y over 2, or Y over 4. Because if X is 1, Y is what? 4. So 4 plus 4. 4 plus 4 over 4, 1. 1 plus this 2. So it means we should have 2 here, right? Let's try. Let's see if the formula I'm trying to remember will work. We also have here y over 2 CO2, and here we have X H2O. You don't remember the formula at all? Y over 2 CO2. Y is now 4, so X CO2 and 1 over 2 H2O. That will be 4 water, right? That will be 2 H2O. 2 H2O here. Then X will be 1, right? Let's see. How many carbons do you have here? 1, 1. How many hydrogen? 4, 4. How many oxygen? So the formula is what? I don't want to ask again and you tell me you have forgotten. Pause it and let everybody cram it. In the presence of UV light, we can have CH4 combined with bromine. The UV light will cause a free radical mechanism for this guy so that by the time this guy cleaves, what kind of cleavage will he undergo? Homolytic. So one Br will come attached to this, from CH3Br plus. So the initiation step is free radical mechanism, homolytic reaction, homolytic fission. Then one of the H's will be abstracted with HBr. Is that okay? On continuous reaction, CH3Br will react with Br2 again, right? So what are we going to have here? CH2Br2 plus HBr. In the first place, what did we form? We formed bromomethane, right? Here we now form what? Dibromomethane. Is that clear? Then the next step, this same guy H2Br2 we react with Br2 again. I hope you understand what I'm doing. I've showed you before, right? In this case, there are 2 H's now and there are 2 Brs. One to react is Br2. This Br2, right? This one will abstract another hydrogen, right? So it will form HBr, and then this next Br will come and attach itself here. So it now becomes C. It was bonded to Br here, was bonded to Br here, and here was bonded to H. So on this side, it's now bonded to what? New Br. So this is now CHBr3. Is that okay? So what does this become? Tribromomethane. Do you understand? So it's the same thing that's happening throughout until we form tetrabromomethane. Do you get it? Alright. So that's substitution reaction. What you are noticing is that what? This guy is just taking the position of hydrogen. That's substitution. Okay? There's no new bond that is formed. Alright. Okay? So what other reaction do we see with alkanes? That's basically it, right? We talked about aromatization, pyrolysis, and all. Is that okay? But we don't need it for jam. So let's go to the next thing. So the next one is alkene. The next one is what? Okay. So with alkene, we said they are generally called what? Olefins, right? What does olefin mean? Oil forming, right? Isn't it? So, and we said that they are unsaturated, which means that they are more reactive. They are more reactive because of the presence of pi electrons. Is that okay? Because of the presence of what? Pi electrons. So the first alkene, because of there is a double bond between 2 carbons, the first alkene is going to be what? Ethene. Is that okay? And ethene has a very good use. One of the uses is that it is used for what? For ripening of fruits. Do you remember? Yes. Alright. So, ethene, how do we prepare ethene in the laboratory? There are 2 major ways, either by dehydration or preparation. Is there anything that we have about, any information about ethene again? We also use it in the production of alkanols, right? So, general of alkene. Alkenes have the general formula CN, H2N, CnH2n, right? Okay, so it means that the first member, if n were to be 1, so you have C1, H2, right? And this does not exist. Is that okay? So it means the first member will have what? 2 carbons. Does that make sense? So the first member is going to be C2 H2 bracket 2, that is C2H4, right? So, and this is what? Ethene. C2H1, 2, 3, 4. Is that okay? This is the orientation. Do you get it now? Now, you see, we didn't discuss stereoisomerism the other time. We didn't. We have to talk about it here. Stereoisomerism. So you see these guys. So the next guy will be propene. Is that okay? Propene is the same. Like for example, see. And what's the difference between them? They're just rotated version of each other. They are what? The same. Is that okay? This is propene. Is that okay? Because no matter where you put the double bond, it will still fall on carbon 1. So this is what? Propene, propene. Do you understand? Okay? Now, let's before we talk about in preparation. How do we prepare them? I said, what is that? What is that? So we said in the laboratory, how do we produce it? By what? Hydrolysis of dehydration. By what? Dehydration of alkanol. Is that okay? The addition of alkanol. Using what? H2. No. By we dehydrate it here using H2SO4. We hydrate it using H2SO4. Is that okay? So how do we dehydrate? So we use ethanol, for example. So this is ethanol. So if we dehydrate this, what does dehydration mean? It means that we remove what? Minus H2O. Is that okay? In the presence of what? H2SO4. Is that okay? The reaction takes place at a temperature of about 170 degrees Celsius. 170 to 180 degrees Celsius. Are you with me? So that's the. So what do we have by the time we remove H2O? Let's remove H2O from here, for example. What will you have? You have how many carbons, how many hydrogens left? 1, 2, 3, 4. So we have 2 carbons and 4 hydrogen. So we can just put what? Double bond there. Is that okay?
Yes, sir.
So this is one of the processes by which we produce ethene in the laboratory. Now, another very important. Okay, which other way do we use to produce ethene? There's one that is also coming to my mind that I cannot remember well. Do you remember? We can also dehalogenate, dehydrohalogenate. Do you remember? Dehydrohalogenation. This is simple. What does it mean? We remove hydrohalogen. Does that make sense? So it means that we must have a haloalkane, right? So let's say we have BrHHHH, bromoethane. So this is a haloalkane, right? The haloalkane comprises of a hydrohalogen, isn't it? Are you with me? So if we dehydrohalogenate it, it means we will remove hydrogen and halogen. Does that make sense? We use KOH to do so. Is that okay? Are you with me?
Yes,
we use KOH to do so. By the time you do so, what are you going to get? You get ethene. Am I clear now? So dehydrohalogenation. We can also prepare alkene. Now let's talk about the chemical reactions. Yes. Okay. Let's talk about the chemical reactions that they undergo. These guys. Let's quickly list them so I will not be having to think too much. These guys also undergo combustion, isn't it? Isn't it? Combustion reaction. But their major chemical reaction, their major reaction will be what? Addition. Is that okay? Because they are unsaturated. Is that okay? Once it is unsaturated, once it has double bond or triple bond, know that it will undergo what? Addition reaction. Okay? And there are two types of addition that it will undergo. You can undergo hydrogenation. You can undergo halogenation. Right? And you can undergo what? Halogenation. Do you understand now? These are the different forms of addition reaction that I can undergo. Another reaction is that I can undergo is what? Polymerization. Do you understand? Now we're going to be doing Markovnikov rule again here. Do you remember? Or Markovnikov rule. Now, polymerization. What are the two types of polymerization? Addition polymerization and what? And what? Condensation. God bless you. Condensation polymerization. But with these guys, what we see is what? Addition polymerization. Okay? Now, what other reaction do these guys undergo? Do you remember ozonolysis? What is ozonolysis? The cleavage of an alkene using ozone. Is that okay? What do we produce? What do we produce? It depends. Is that we produce an alkanal or no, usually we produce alkanal because the O will stick to the end. When we do it, you will remember. When we do it, you will remember. And let's quickly go over each one. I'll be fast, so follow me fast. Is that okay? Follow me as I speed up. That's what I mean. Okay? So the first one there is the combustion reaction. First one is the combustion reaction. Basically, we say it burns with what? A smoky flame. Do you remember? Alkene burns normally, but alkenes, they burn with what? Smoky flame. Don't forget that too. That's, we differentiate them from alkenes too. So we have, for example, our classical guy here. As for example, is going to be ethene. Does that make sense? So C2H4, does this make sense? Plus O2 will give us what? CO2 plus what? H2O. Typically, once there's an excess supply of oxygen, you always produce what? Combustion reaction will always give you of any hydrocarbon. Combustion reaction of any hydrocarbon always gives you what? CO2 plus what? H2O, ideally. Is that okay? So when you hear any hydrocarbon, be it carbohydrate, be it fat and all, as far as they are undergoing combustion reaction to oxygen, they are going to form CO2 plus H2O. So that's that. Now the addition reactions. Let's talk about first hydrogenation. For the hydrogenation, basically we are talking about C, that's CH4, right? It wants to react with H2. Now, this is hydrogenation. So H2 is basically H to H, right? So what happens? These two will come and break this bond. But the process is catalytic, right? What catalyst we use? Palladium or what? Or platinum, right? Or nickel, right? Does that make sense? Okay. So when we hydrogenate, what do we get? We get what? If this was ethene, what do we get here? Ethane. Why is there no response again? Ethane. We get what? Ethane. Do you understand? Okay, there is a classical type of addition. There is reaction with bromine water. Reaction is what? So it's a type of hydrogenation, but so we'll consider it because it's one of the tests for alkene. Is that okay? It's one of the tests for what? Alkene. So let's first talk about halogenation. So in halogenation, we basically what? React this same ethene. We basically react it with a halogen. Say Cl2 for example. What are we going to get when we react them? I will get C, H, Cl, H. Is that okay? It's clear, right? Okay, so what would this form? This is what? 1,2-dichloroethane, because now single bonds all through. Are you with me? This is what? Halogenation. This is what? Because we halogenated the alkene. Halogenation. Now let's talk about hydrohalogenation. With hydrohalogenation, don't forget the catalyst, please. With hydrohalogenation, so there are two forms. Is that we use an acid, or we use acid water. So this is, for example, acid water here is going to be HBr, HOBr. That is general bromine water, HOBr. That will be mono. How do you name it? Monooxobromate 1. Oxo. How do we name it? For HCl, hypochlorite, right? Basically, leave the name. Leave the name. Hydrohalogenation now. Hydrohalogenation. So basically, we have C double bond C. Is going to be reacting with hydrohalogen, such as HBr. Now, in this case, there are two ways. Now, for this one, it's very easy. Once the bond is cleaved, what do we form? We will form C to C, then our two H's that were there before. One of these H will come here. Is that okay? And the other guy, Br, will come to the next guy. And then we have our two H's. So what will this be? Bromoethane. Is that okay? Bromoethane. But what if it's not a symmetrical alkane? A symmetrical alkene. For example, if we are going to hydrohalogenate this guy, C double bond C. So here, was HBr. Now, which of the following products will be formed? We have two possibilities here. Is either we have this CCC, CCC. Is either we have this. Now, following Markovnikov's principle, Markovnikov's principle, which of these following products will be formed? Using Markovnikov's principle. What does Markovnikov's principle say? He says that there are two components here. So the hydrogen will go and join to one of the carbons that has more hydrogen. Does that make sense? Or we say that the heavy group will go and join the least substituted, the most substituted rather, carbon. Does that make sense to us? The Br, which is the heavy group, will join the most substituted carbon. What is the most substituted carbon? This carbon, isn't it? Substituted by this and this. Or secondary, if there was tertiary there, what will happen to join the what? The tertiary rather than the secondary. Does that make sense? Because I told you that it's the ease of formation of carbocation that determines which one will be formed. Is that okay? We don't ever have primary carbocation. We always have a secondary carbocation. So what you can have not always. You can have a secondary carbocation because if this bond cleaves, I'm going to have a plus here. Is that okay? So if we have I'm going to have a plus here or a minus. That's carbanion. Is that okay? But basically, the idea is that this thing is going to stabilize the bond. It's going to stabilize the intermediate that is formed. The two of them, they are going to use what effects to stabilize? Hyperconjugation effects. Okay, so now which of the products is possible? Markovnikov rule says that the hydrogen we add on to the carbon. We want to cleave this bond here. When we cleave the bond, the hydrogen should add on to the carbon that has the highest hydrogen. So if the carbon must be added, the hydrogen must be added to the carbon with the highest hydrogen. Which of these products is formed, Abiodun? The hydrogen component of this guy we add to the carbon with the highest hydrogen. So when this bond breaks, which of these products will be formed? A or B? A, right? Okay, let's see. So once we cleave this bond, which of these two guys has more hydrogen? Is it this guy or this guy that has more hydrogen? Okay, this guy has more hydrogen. So let's count how many hydrogens are around it. One, let's do two. Please tell me, what's the answer, please? What's the answer? And which of these are the Markovnikov products? This one, right? Is the Markovnikov product. Okay. There is. No, Uti. Which of these will be the Markovnikov products? Which of these, A or B? A will be the Markovnikov products. Okay, how about you? B. Okay. Martin, which of these will be the Markovnikov products? B. Why?
Because it has this one has the highest hydrogen.
God bless you. So this guy has more carbon. This carbon has more hydrogen. So this guy will be attached to this guy. Then the Br will go and join carbon. So the answer is this guy. Are you with me now?
Yes, sir.
Maybe, what's it? Maybe we should take bromine water is this. HOBr. Now, addition of bromine water follows almost the same process. Is that okay? Only that in this case, first is bromine water that we use to test for the alkenes, because it's going to give us, if bromine water is added to alkene, for example, like this, plus HOBr, just follow the simple thing. Come and break this bond, put OH in one, put Br in one. Does that make sense to us? Very simply. Very simply. So who can write it here? So, and one thing with this is that, what's the color of bromine water? What's the color of bromine now? Brown now. As we go down the group, do you remember? So, we say if we come from fluorine, what's the color of fluorine? Colorless, yellow, greenish yellow, brown, that's from fluorine, colorless, greenish yellow chlorine, bromine, brown, astatine, iodine rather, blue black. Do you understand now? Okay, so this guy is brown, bromine water. So this guy, alkanes, they decolorize bromine water to be decolorized, and that's one of the tests for alkene. Well, basically test for unsaturation. So it means that alkyne too can decolorize it. Alkyne that can decolorize. The only difference now, the test we use to differentiate between this guy and this guy, alkene and alkyne, is that we take it through. Alkynes are the ones that can turn copper, a particular copper solution, into reddish color. Is that okay? So you see a question that there's one ammoniacal something, I can't remember that thing. But you are most likely to be asked this rather than that. Okay, so it's test for unsaturation. Is that okay? Now the next one is what? Polymerization. And here it always undergoes what? Addition, polymerization. So you basically see something like that looks like this. Right? So when you see something that looks like this, we say N this guy, right? When it polymerizes, what is going to form? It's going to form plenty C's Cis, this one will be, do you remember that structure? I won't draw it again. But the point is that it's going to polymerize. It's going to polymerize. Polymerization means this single unit is called a what? A monomer. Is that okay? And to form larger units called what? Polymer. Is that okay? Some example of polymers: polyvinyl chloride, polystyrene. Do you remember? Know their uses. So is that okay? Know their uses. Okay. Now another kind of reaction that it undergoes before we treat ozonolysis. Let's talk about the way this guy is formed. Alcohol, a particular alcohol. We can form alcohol using alkene by hydration of alkenes. Is that okay? Hydration of alkenes will give us an alcohol. And the alcohol that is formed, is it hydration of alkene or hydration and oxidation at the same time? Do you remember? It's hydration and oxidation. I know you must have forgotten. Now it's reaction with potassium permanganate. Is that okay? Do you remember the one that? Yes, I mentioned it just now. That we said it will decolorize. It will change the color in basic solution. What's the color of potassium permanganate normally? Purple, right? So in basic solution, what will happen? To change to what? Green. Then in acidic solution, the purple will change to what? Colorless. Don't forget to. So if we take this guy, a particular alkene, please watch. The product is very important too. If we take any alkene, for example, ethene in this case, to react with H2O in the presence of what? Potassium permanganate. What you will get will be CCOH. Does this make sense? So what is this? What is this? 1,2-di. Ethane, 1,2-diol. Does this make sense? And what is the common name, general name of this guy? Ethylene. God bless you. So what did we say we use it to do? We use it to prepare what? We use it for antifreeze in car engines, and we said our car radiators, and we said that it is also used to form tyrylene. Is that okay? Tyrylene is also used to make polymers. Do you understand now? Okay, so that's the case. Don't forget to ethane 1,2-diol is ethylene glycol. Is that okay? And then it's used as an antifreeze. Okay. So in acidic condition, this guy will change from purple to green in basic. In acidic condition, you have this. Is that okay? Then let's go over the last one, ozonolysis. Are you following me?
Yes, sir.
You have a question? Yeah. Okay. Yes, because since it's basically oxidation here, Since it's basically oxidation here, it means you can also use K2Cl2, but I don't know the color change. But since it will decolorize in acidic condition, I think that guy too will also what? Decolorize. But usually from alcohol, do you remember when we said, okay, the condition will be the same. Do you remember? If you oxidize, that's from alkanol to alkanal, not alkene. Do you remember? If you use K2Cl2 to oxidize alkanol, primary alkanol, what do you get? Alkanal. Do you remember? So that K2Cl2 will go from what? Orange to green. Do you remember? And potassium permanganate will go from purple to colorless. Do you remember? And so that's what I was thinking. But I think you should be able to use K2Cl2 because it's basically oxidation here, isn't it? All right. Then, when we did reduction there, in the other case, we can also prepare this thing. Prepare alkenes, I forgot, by reduction. We can also prepare by reduction of alkenes. Is it reduction of alkenes itself? Yeah, I think reduction of alkenes. Using strong reducing agents like LiAlH4 and NaHB, is it B4? So these are very strong reducing agents. Is that okay? I think you can use it to also prepare alkenes. When we reduce alkanes, just basically we are subtracting 2 hydrogens. Do you understand? When we subtract 2 hydrogens, we'll get our alkene, corresponding alkene. All right. Then ozonolysis. What is ozonolysis? The cleavage of what? Cleavage of alkenes using what? Using O3. Is this clear? So for example, let's use one that is asymmetrical. So if we cleave this guy, let's cleave this guy. This is how you cleave. See, very simple. Or very simply, draw a long line. Cleave like this. Is that okay? Then put O here and O here. Do you see where I did it? So the product that will be formed there will be what? 1, 2, 3, double bond O. Does this make sense to you now? What's his name? What's this guy? Propanol. Do you understand? Are you with me? Then in this case we have 1, 2, double bond O, H. What's the product that we formed? Ethanol. Do you understand now? Okay. What will be the product of cleavage of butene? What will be the product? Or ozonolysis of butene? You don't have to write anything. Butene. God bless you. 2 ethanol. All you just do is, you see that double bond in between them. Butene means that is symmetrical, right? When you cleave here, you have ethanol, ethanol. Does that make sense now? Very simple. Just do it like that. Put your O here, 2 I's there. Do you understand now? You haven't put dots. Do you understand now? Yes? An empty conical flask. How many gig? 4.1 gig. We're going to the next one. Epoxies, right? Leave down and they will read it on their own. We said that there's usually an empty conical flask that is placed in between the first product and the product that collects here. What's the product that collects here? I can't remember. But I remember that this guy is put there to prevent what? Back sucking. To prevent what? Back sucking of the gas. Is that okay? So that the gas will not suck back. If it was into this thing directly that was here, it will suck back this thing. Is that okay? So we put this here to prevent back sucking. Okay. Now, so we're done with. So the test for unsaturation is what? Decolorization of bromine water. Okay. So what's the next guy? Alkynes, right? Alkynes. And usually this one, there's not much. It's just what we have treated before occurring twice. Do you understand? So the reactions that we talked about, hydrogenation, this one will occur what? Twice, isn't it? So that will be hydrogenation will first give you alkene, then you hydrogenate again, alkane. Is that okay? Then for halogenation, twice again. Should I show you? You will know it, right? Okay. So basically this one to decolorize bromine water, all right. So because it's unsaturated. Now let's go to the next set of so those are hydrocarbons we just finished. Is that okay? Let's go to other organic compounds, including beginning with alkanols. Is that okay? Let's begin with alkanols. Now, what are alkanols? They are basically what? Alcohols, right? Now, there are 3 groups of alkanol, depending on the there are 3 types of alkanol. We have the mono what? Hydric alkanol. We have the dihydric. Give me an example of monohydric. ethanol. Why? Because OH group is just one there. Is that okay? So this is alkanol, monohydric, only one all. Does that make sense? Dihydric, there will be two, right? E.g. ethan 1,2-diol, ethylene glycol, antifreeze agent, right?
Yes, sir.
Okay, that will be two H groups, two OHs. Does that make sense?
Yes, sir.
Then the other one that we get from that we use in the saponification, is that okay? So trihydric, is that okay? E.g. give me what? Propan 1,2,3-triol. Okay, there was one, 2, 3 that we should talk about. Octane. Do you remember octane number? Do you know we did not talk about it? Let me quickly talk about it. Octane number refers to the anti-knock property, right? The anti-knock property of a particular fuel. So fuels that knock engines are fuels that burn, they don't burn completely. Is that okay? They don't burn completely. So they have knocking property, and those fuels are N-heptanes. N-heptanes are bad fuels. Is that okay? So we give this one number 0 octane rating, and we give this guy isooctane. What is isooctane? Isooctane. 1,2,3-trimethyl. You have forgotten. 1,2,3-trimethyl propentane. Let's draw it. Let's see. 1, 2, 3, 4. 1,2,3-trimethyl propane. So it's called isooctane. Yes. 1,2,3-trimethyl. Is it not pentane? It's pentane, right? But if it's 1, 2, 3, leave the structure. The name is what? 1,2,3-trimethyl pentane. This one is giving 100 value, 100 in octane rating. So the best fuel is the one that has what? 1,2,3-trimethyl pentane. Is that okay? All right. One other thing that we didn't even mention is in alkene are the types of alkene. I told you about cumulated alkene, conjugated alkene, and what? Isolated alkene. Okay, but basically, so that's about octane rating. So this improves the anti-knock property. Is that okay? This guy. And N-heptane has poor force. God bless you. So propan 1, 2, 3-triol. Okay. Now, based on where the OH group is, monohydrics are classified into what? 3. Which are what? Primary, secondary, and tertiary alcohol. So the primary alcohol, they have the carbon that is attached to the OH is attached to only one carbon again. Do we get this? So this is the carbon bearing the OH. This is the carbon bearing the OH. How many more carbons is it attached to? One, right? So this is a primary alkanol or primary alcohol. And the idea is this. When you oxidize primary alcohol, what do you get? Alkanal, corresponding alkanal. So if you oxidize this using K2Cl2 or KMNO4, what do we get? This guy. What's the name of this guy now? Propanol. Is that okay? Because it's propanol, so we get propanol. What if we now oxidize this? This is a secondary alkanol. Why? Because the carbon that is attached to the OH is attached to 2 other carbons. 1, 2. Here, the carbon attached to OH attached to only one carbon. Primary. Carbon that is attached to OH attached to 2 other carbons. Secondary. Is that okay? Yes. Oxidation of this one will give us what? Alkanone. So oxidation of this, what's the product we'll get itself? Propanone. Does this make sense? Then tertiary are the ones that look like this. So this guy now, the carbon that is attached to the OH is attached to 3 other carbons. 1, 2, 3. So when you oxidize this, what do you get? It cannot be oxidized further. Is that okay? It cannot be oxidized at all. But here, we can further oxidize this guy. When you further oxidize alkane, what do you get? Alkanoic. Is it clear? So it means you can oxidize primary alcohols twice, secondary alcohol once, tertiary alcohol never. Is that clear? Now, how do we distinguish between them? Which test do we distinguish between them? Lucas test. Lucas test. Now, Lucas test is just zinc Cl in HCl or zinc in HCl, something like that. They are combined together. So when you add zinc Cl in HCl, or you add Lucas's reagent, is that okay? Lucas's reagent, you add it to a primary alkanol. What will you notice? Turbidity immediately, right? The alcohol will become turbid or cloudy immediately, right? If you add it to a secondary alkanol, what will happen? It will take time to become cloudy. If you add it to a tertiary alcohol, what will happen? It will not go cloudy at all. Do we understand?
Yes, sir.
Okay. We're almost done. Do you see that? Now, now let's go to alkane and alkane. What are the functions? Okay, laboratory preparation and industrial preparation of our ethanol. But that one they normally ask too, right? We're almost done. Just calm down. We might stop at and calm down. Are you still with me?
Yes, sir.
Are you happy with me?
Yes, sir.
Are you happy with me?
Yes, sir.
Let me hear that yes. Let's be loud. Are you happy with me?
Yes, sir.
Abiola, are you sure? Okay. Let's go. Okay. Kenny is always happy with me. Let's go. Ethylene did what? Came to your house, right? Then industrial preparation of laboratory preparation of alcohol. Industrial preparation of alcohol. Now, industrial preparation of alcohol is called what? Alcohol fermentation. Is that okay? So we are going to get our molasses. Is that okay? It's prepared from molasses or any starch. Is that okay? So that molasses is going to contain C10H12O11, right?
Yes, sir.
And this starch, right?
Yes.
Starch that is what kind of condensation occur here? What kind of polymerization occur here? Condensation, polymerization. Is that okay? That's what brings about that long starch chain. Is that okay? Now, what do you call that condensation, polymerization? That bond between them is called what? Glycosidic bond. It's called what?
Glycosidic bond.
It's called what?
Glycosidic bond.
All right. It's okay. So this guy, you now react it with what? Malt, right? Isn't it? You cook it with malt that you get from barley, not maltina, right? With malt products such as barley, right? So when you cook it with that guy inside it has what? Diastase, isn't it? So diastase will break this guy down to what? To what? To a particular C20 H22 H24 O22. Is that okay? So this guy will now further break down to this guy by the action of this is not diastase. This is maltose inside malt, right? Maltose is inside malt, so it's maltase rather. Maltase will break this guy down to this guy. Is that okay? Are you with me at all?
Yes, sir.
So then C20H24O22. So this will now be like a no, this is not a monosaccharide. This is like a disaccharide. Is that okay? This is a disaccharide. So this guy, yes? The name of the disaccharide? This guy? and the name, right? This guy will be, so if this is starch, this guy will be sucrose. What's sucrose? Sucrose contains what? Let's talk about the distance we have. We have lactose, we have maltose, we have sucrose. Sucrose is what and what is inside sucrose? Glucose and fructose. Inside lactose, galactose and glucose. Maltose what? Double glucose, God bless you. So this is maltose. Does that make sense now?
Yes, sir.
I think there is a number here. I can't remember these formulas. So this guy will now be broken down by diastase. Does that make sense?
Yes,
To give us C6H12O6. Is that okay? Are you with me?
Yes, sir.
So by the time that happens, another, we call it anaerobic fermentation too. Okay, so that when I mention anaerobic here, so this guy C6H12O6, this is what happens in our own system too. In our system, the enzyme that acts on it is invertase. Is that okay? Inside us, but in the industrially they use yeast. Is that okay?
Yes, sir.
What is inside yeast? Zymase. What enzyme rather? These are enzymes. Is that okay? When you have these are enzymes basically. Is that okay? When you have A's, anything that ends with A's, biology is what? Enzyme. So this enzyme will now break this guy down to what? C2H5OH. You understand now? And this is what? Ethanol. Does this make sense?
Yes, sir.
Okay, that's the way it is prepared. Plus CO2. Yes, thank you. Now, but the point is this. This is the minor product. So, but the point is this. This thing that is produced here is very dilute. Is that okay? So to concentrate it, they usually add it to. How do you concentrate it? Basically, no. There's also, I didn't mention. Did I mention wood spirit? Now, wood spirit is methyl alcohol. Is that okay? We said if it's ingested, what will happen? Blindness, right?
Yes, sir.
Wood spirit, methyl alcohol. So that's what CH3OH. Does this make sense? Methanol. So that's wood spirit. So this spirit, when it is concentrated, it forms what? Rectified spirit. It forms what's called what? And rectified spirit is about 95. This one, the spirit that is formed, the spirit that is formed here is dilute. It's about 6%. 6% ethanol. Very dilute, right? By the time you concentrate it, I think by adding it, no, you now dry it. As you dry in quicklime. Is that okay? Use quicklime to dry it. So that's when you now form absolute spirit. Is that okay? And that time to be about 99% pure. Is that okay? 99% ethanol. Do you get it? Okay, so but rectified spirit, that's it. Do you get it? Please go through those notes, Go through those notes. What have we not talked about ethanol? We mentioned the test. What other thing? What's the test? Okay, that's the test. What else again? Chemical reactions of alkanol. And we have talked about laboratory preparation. That's what? Esterification reaction, thank you. We'll not talk about esterification reaction. Do you remember the laboratory preparation is simple now? Just what? The acid hydrolysis of ethene. Do you remember? Hydrolysis of ethene will give what? Ethanol. That thing we did. H2SO4 plus H2O. You understand now? To give you what? Ethanol. That's the laboratory operation. I will say the temperature is about 170 degrees Celsius, yeah? Okay. So, what else? What else? Esterification. Thank you. So let's talk about ester. Esterification. Now, with esterification, what is esterification? It's the reaction between what? Alkanol plus alkanoic acid to give what? Alkanoate, known as what? Ester. And what? And water. Is that okay? It's very simple to write. I've showed you this before, right? If I use ethanol as my alcohol, and I use methanoic acid, for example, let me use methanoic acid as my alkanoic acid. Now, here's what we produce. We produce ethanoate. And now look at the way to be. Look at the way to be. Just come and take this guy here and take this guy here. Does that make sense? Once you take this guy, what have you taken? Water, good. I've taken H2O. What do you have left? You have this guy left, CHOO. So basically it's double bond O. And you have this guy who come and join here. Are you with me now? So you now have C double bond, CH and CH3. Is that okay? So this one has a different way of naming it. What would this one be? Ethyl methanoate. Does that make sense?
Yes, sir.
Is it clear?
Yes, sir.
Ethyl methanoate. Okay, that's the case. OH is always the alkanoic acid, that you use. Is that okay? All right, then let's talk about alkanal and alkanone, aldehydes and ketones. Let's basically go to the part that they usually ask questions about, aldehydes and ketones. Now, which one is reducing sugar? Aldehyde. And the test for reducing sugar is what? Silver mirror test using what? Tolle's reagent. Is that okay? Tolle's reagent. Tolle's reagent is just silver AgNH3 2 plus. Remember this? So by the time you add this to a solution containing aldehyde, alkanal or alkanone, alkanal is the one that will form a silver mirror. To form what? Silver mirror. Are you with me now? So that's silver mirror test. So alkanone will not form silver mirror. Alkanone will not. This one is the reducing sugar. These ones are not reducing, non-reducing sugar. Reducing sugar, non-reducing sugar. So an example of this one is fructose. Do you remember now? But this one is what? Glucose. It's reducing sugar. Are you with me now?
Yes, sir.
What other thing do you get tested on aldehyde and ketones? What other thing? Felons. Okay, yeah. So all those other reactions that we talked about. What are the? Okay, let's go to the class, the food tests. Open your notes to food tests and let's list them. And we'll round off the class. Is that okay? What are the food tests we have? Go. Go on. What are the food tests you have? We have carbohydrates. For carbohydrates, what do we have? Benedict test. What's Benedict test? What is the color change for Benedict test? It changes to what? Brick red coloration. Okay. How about Felins, right? Felin. It's Felin, right?
Yes.
Felin's reagent. What's the color change now? Brick red too. Felin's reagent. Blue to brick red. How about Benedict? Benedict's reagent. So list them like that. Brick red, PPT. Which other one? Sucrose test. Brick red too. I think that will be the one for felling. Felling from blue to what? Brick red. Which other one? Start test. Blue black correlation. And the one we did with the one they do with leaves. Do you remember? What's the name of the test? Iodine, right? Iodine, yes. Iodine test. Iodine test, you said, goes to what? Blue black coloration. Carbohydrates. Okay, that's all for carbohydrate. Okay, protein, Burette, yes. Burette test. Purple color. Xanthoprotein. Yellow coloration, Fats. Emotion. Cloudy what? White. Sudan 2 test. Is it Sudan 2 or just Sudan? Sudan 3. Okay. I didn't know that. Red stained oily layer. Which one again? Vitamin C, leave down. Yeah, leave down. Alright, so with this, we have come to the end of the uses, ester. What are the uses of ester? Perfume, seasoning, disinfectant. Use them for disinfectant. I doubt it. It has sweet smell now. How can you use sweet smell for disinfectant? For soap, yes, for soap, better know it. Is that okay? Perfumes and soaps and those guys, and for soap making, is that okay? Right. So that will be the end of this class. Do want to subscribe to the channel if you have not already, and God bless you as you do so.